Well, good afternoon. The title of my talk was taken by Tini Veltman, so I changed it to The Future of Fundamental Physics, but there's really not much difference. Elementary particle physics is the discovery and understanding of the basic building blocks of matter and the forces that act on them. That is expanded after the success of the Standard Model to include our understanding of gravity, dynamical space-time, and therefore cosmology and the history of the universe. And I'll be discussing very briefly all of these subjects in very little time. But let me start as Carlo did, and with the Standard Model. The culmination of literally a few thousand years of trying to understand the atoms that make up the matter, everything we see around us, and the forces that act on these atoms. And we've ended up with what is called a model, but is really the most comprehensive and precise and quantitatively descriptive and test theory that we've ever had in physics, which, on the one hand, describes the basic constituents of matter as consisting of quarks, up and down quarks that make up our nuclei, and electrons, then their partners, neutrinos, that make up atoms together with the nuclei, and two other families of quarks and leptons, which have been discovered. And most importantly, the forces that act on the quarks and the leptons, generalization of Maxwell's theory of the electromagnetic interaction, which we all learned in high school, when generalized to consider theories or objects, particles like quarks and leptons that carry not just electrical charge, but other charges, weak charges, which come in two varieties, and strong charges, which come in three varieties, we call them colors, describe all the forces that act within the atom and the nucleus, with the exception, of course, of gravity, which acts everywhere, but is quite ignorable at ordinary scales. Together with the ingredient that Carlo focused on, it was discovered just exactly 7 years ago, is that right? I think on July 4th, the Higgs particle, which completes the Standard Model and still is largely unexplored or unconfirmed. But now this effort, which, as I said, has really been going on for thousands of years, required the work of countless theorists and experimenters over centuries, but especially the last century, and has been responsible for 52 Nobel Prizes, Nobel laureates, 30 Nobel Prizes. This is not the work of a few people. This is not like Einstein's theory of gravity. 22 of them were in experimental physics, 10 in theory. You can take that as a lesson that it's harder to win a Nobel Prize in theoretical physics. 5 are present in this room. Here they are, starting with J.J. Thomson, Chadwick, Lawrence, Yukawa, theorist, Yang and Lee, Schwinger, Feynman, Gell-Mann, Glashow, Weinberg, Salam, Cronin and Fitch, Carlo Rubbia, whom you just heard, Tini Veltman, who gave a talk this morning, and so on, down to Kajita and McDonald, the most recent prize in this field, who are both present. So this is the work of physics over centuries, culminating at the end of the 20th century in a comprehensive standard theory. It is beautiful. Those of us who understand it a bit know what I mean. For others, it might not look so beautiful, but believe me, it is. It's based on deep symmetry principles, quantum mechanics, relativity, and local symmetries of nature. It contains uncalculable within the standard theory parameters, but not too many. For ordinary physics, what we see around us, 1 or 2 parameters suffice to, in principle, calculate anything that has been measured on Earth. Not the properties of dark matter, which so far have only been seen out there in the universe, to, in principle, arbitrary accuracy, and in some cases, accuracy of 1 part in a trillion, and in many cases, thousands of experiments to better than 1% or 0.1%. Together with classical general relativity, Einstein's theory of gravity, we have a rather complete, unbelievably complete and successful fundamental, that's what I mean by fundamental, reductionist sense, theory of what the world is made of and how its components act on each other and create structures like us. And this theory, in this sort of reductionist sense, works, as far as we can tell, perhaps down to distances which are unimaginably small, the so-called Planck length, and to the edge of the universe. The behavior of nuclei and atoms anywhere in the universe obeys the same laws. It's quite amazing, 60 orders of magnitude. And we desperately search for deviations from this theory in order to answer questions that we can't yet. And that's where the frontiers are that I'll briefly mention. If we look at this Lagrangian, which enables you in principle, if you know quantum field theory and you have big computers, to, in principle, calculate everything, there are a few parts of it which aren't so beautiful. For example, the values of the quark and lepton and neutrino masses and their mixings have to be put in by hand, measured, and put into the theory. We would like to calculate them. That's a theorist's wish. That's a theoretical problem. Theorists are arrogant. They would like to calculate everything, understand why it is so, why it can't be changed. But from a practical or experimental point of view, this is the way it is. Some numbers have to be measured and can't yet be calculated. There are other issues such as this parameter in the theory of the nuclear force that violates parity time reversal and is very small. We have conjectures as to how that makes sense, but they're not totally confirmed. There are other elements here, the properties of the Higgs particle, which we would like to understand from some deep principle. We don't. And of course, part of the whole theoretical scheme is gravity, which so far we only understand, have tested, observed at the classical non-quantum level. And as we discussed much yesterday, dark energy as well, which governs the large-scale structure of the universe. But this is the theoretical framework of theoretical physics, with a very specific theory, most of whose parameters are well measured, and in principle, one can calculate just about anything. Let's see. I wanted to concentrate on my favorite part of this theory, QCD, to which I'm especially proud of, where it was discovered in the end that the strong nuclear force that we now understand holds quarks permanently together inside the neutron and the proton that make up the nuclei of our atoms is mediated by a field much like the electromagnetic force is mediated by the electromagnetic field. In this case, there are these quarks carry three charges, red, white, and blue, we call them. And the force between them at a classical level, were it not for the strange quantum mechanical properties of the vacuum pictured here, full of quantum fluctuations of chromodynamic fields and virtual particles popping in and out of existence, would obey a 1/r² Coulomb's law, and we could easily ionize the proton and the neutron, and pull the quarks out and make them run in wires and have quark motors and all sorts of wonderful things. But we can't. No one has ever seen a quark. And that, we understood, is because the vacuum, the properties of the quantum vacuum, which is like a medium, strange medium, squeezes the flux lines of force into a tube. And if you just apply Gauss's law to flux lines that are squeezed into a tube, you will find that the force between the quarks does not decrease with distance. And the energy to separate them increases without limit. This is known as asymptotic freedom. It also explains why the quarks at short distances, asymptotically short distances, are freely moving, the observation that led to this theory. Here is a simulation of what happens when you pull a quark and an antiquark together. You see how the lines of flux are squeezed into a tube. And that leads, as I said, to what we call quark confinement, which is why no matter how hard you smash protons together, quarks never come out. If, however, you were to heat this room to 100 million degrees, protons, neutrons would melt and the quarks would escape. And that has now been achieved in the laboratory for very short times in heavy ion collisions, where we see a phase transition in the behavior of the vacuum that is confining the quarks inside nucleons. You'll notice that these flux tubes look like fat strings. And indeed, string theory, which is 51 years old, originated in an attempt to understand properties of nuclei, of the strong interaction. And they were led by the data to conceive of a theory of extended objects and strings. And that, we believe, is another way of describing QCD and much more. But what lies beyond the standard theory? We have a few, not many, experimental clues: dark matter, which we discussed at length yesterday, neutrino masses, whose spectrum and properties we're still measuring, the asymmetry of the universe, the fact that matter is predominant, etc., the cosmic acceleration. We have theoretical challenges to unify the forces, to calculate some of these masses and the scales of the weak interactions, and of course cosmological questions, vacuum energy, dark energy, understanding inflation, and so on. And we do turn more and more to cosmology and astronomy and astrophysics to give us such clues. We've heard yesterday how enormous advances have been made in understanding physical cosmology from almost the beginning till now, a marvelous standard theory or model of the universe. But it has revealed, it and other measurements, observations have revealed, as we discussed yesterday, the existence of dark matter, dark energy, and that's a challenge for theoretical physics to explain the nature of dark matter, to test our ideas about dark energy, for sure. But even a larger challenge is to go back to the very beginning. The models that theorists use to try to understand the cosmic microwave background that we see go back almost to the beginning, to nanoseconds after the so-called Big Bang, or the beginning of the universe, whatever that means, where all our equations and approaches so far break down. That is one of the major challenges, to say the least. We are now at a point in time where the question, how did the universe begin, is a scientific question. Reasonable papers can be written about it. Reasonable ideas have been put forward. Can physics really determine the initial condition of the universe? We don't know. This is not a question that physics has ever been challenged to ask before or had the observational, experimental, and theoretical tools to answer. And equally important, in my opinion, as the laws of physics seem to be completely invariant under time reversal, how will the universe end? Coming back to particle physics, from the beginning of the Standard Model, theorists extrapolated the model to ever shorter distances or higher energies. It's easy to do for a theorist. It's not easy to do for an experimenter. And the amazing thing is that the forces we know, the three forces that act within the atom and the nucleus, appear to come together, have a common origin at extraordinarily high energies and extraordinarily small scales. And even more remarkable, that is the same scale of energies and distance where gravity becomes a quantum force, and we lose our classical understanding. Strongly suggesting that all the forces of nature, those that we know about at least, are unified at this scale. And an exciting prospect. And leading us to focus on string theory, which offered the possibility of naturally unifying these forces at the so-called Planck scale. As I said, string theory arose from trying to understand mesons, or properties of QCD now, of strongly interacting particles, described in terms of open strings, flux tubes with quarks at the end. But it was early discovered in that approach that you could close an open string and make it a closed string, and that the properties of closed strings gave rise at large distances, low energies, to Einsteinian gravity. And that was one of the most exciting remains of string theory, to have a consistent theory of gravity unifying all the forces of nature. And it still remains a very open question whether that direction will succeed eventually in describing all these particles and forces coming from one object in a unified way. But that physics, unfortunately, is at the Planck scale, which Planck, introducing the quantum of action, Planck's quantum constant, realized defined the fundamental units of length and distance and energy or mass. That's why we call them the Planck units: velocity of light, Planck's constant, and Newton's constant. And those define the fundamental length scales of physics. Unfortunately, they're extraordinarily far away from everyday experience and everyday accelerators. It's what I call the curse of the logarithms. I'll explain. We've learned in the standard theory that the ordinary forces of nature act at a logarithmic scale. Things only vary slowly as you go up in energy or down in distance logarithmically. So on a logarithmic scale, in the last century, we have gone from the macroscopic world to understand atoms, the nuclear scale, the strong and weak nuclear scale, and on a logarithmic scale, understanding physics at the Planck scale is a similar jump. We could surely finish it in a few dozen decades. Unfortunately, our ability to measure and observe physics does not grow logarithmically with energy or distance. Dollars grow more like energy squared, if one is hopeful. That's the exponential of the logarithm of energy. And on that scale, going from Fermilab to the LHC is a big jump. Going to the future colliders that Carlo talked about is another reasonable jump. But the Planck scale instrument, microscope or accelerator, I'm not sure what direction that is, but it's many, many kilometers that away. It seems impossible to imagine directly measuring physics at the Planck scale. So what should we do? Well, at the moment, we must fully explore the next step, which is well within our reach and capabilities, and there are many plans to do so. As Carlo discussed, a very new technology with a muon collider, but with standard technologies, one can certainly build a 100 TeV collider at CERN. It's one of their plans under discussion, as well as new countries with great resources that are coming into the game and might do so, for example, in China. Theorists, on the other hand, can proceed with trepidation into the dark, and they often do, encouraged by Einstein, for example, in his beautiful quote where he says that his successful attempt to derive delicate laws of nature along a purely mental path by following a belief in the formal unity of the structure of reality encourages continuation in this speculative direction, the dangers of which everyone vividly must keep in sight who dares to follow it. Well, we should be very careful, but proceed. And we are proceeding to do what must be done, namely unify the theoretical framework by understanding the quantum nature of gravity, of dynamical space-time, which if you just apply quantum mechanics to Einsteinian gravity, you find wild fluctuations of space and time itself at this characteristic distance. Everything breaks down. We must go beyond Einstein's theory, which he himself tried to do often and would applaud. And we challenge our notions of space-time. String theory has reminded us that it's an open question as to whether there are more dimensions of space. Totally possible. Very interesting possibility. Early attempts to quantize Einstein's theory have led to strange properties of black holes, which we now know are abundant throughout the universe, and which seem to violate the basic principles of quantum mechanics. As you drop correlated information, say entangled pairs of quanta, one falls into a black hole, one qubit does, black holes evaporate, you're left with a mixed state. Information is lost. That violates the basic principles of quantum mechanics, and understanding black holes in a fundamental way has been at the center of our Gedanken experiments for quantum gravity for decades. In the last decade or two, string theory has taken a turn because of the discovery of a profound duality between descriptions of nature, of certain physical phenomena, in terms of these open strings like the mesons, which end on what we call branes, on surfaces, and closed strings which describe gravity. And we have established with great confidence the dual equivalence of totally different looking, sounding descriptions of nature. Quantum mechanical descriptions without gravity and strings in a larger dimensional framework. This seems to have resolved the black hole paradoxes. For example, the Hawking's idea that black hole formation and evaporation would violate quantum mechanics seems to be shown to be wrong by constructing exact duality between well-understood information-preserving processes like the formation of quantum quark gluon fireballs, which can be done in the laboratory, and black holes. Even Hawking agreed that information is conserved. There are other important applications of these ideas. I'll pass over them. Most exciting, string theory challenges many of the notions of space-time and suggests that space-time is better thought of as an emergent concept, as well as gravity. That's very difficult to understand, just like the origin of the universe is difficult to understand. And I would like to end with if granted, with a very short question, because some of you might be a little taken aback by the arrogance of theoretical physicists who try to understand what is space-time made out of and how did the universe begin. Can we really go on doing this kind of fundamental physics forever? And one reason we might not be able to go on is that we'll come up with the answer and construct a final theory. But there's another reason we simply might not be able to. Are we too dumb to answer how did the universe begin? More importantly, I think more likely is we might lose the will to proceed. So is there a final theory of physics? This is a question that I like to pose in geometric terms, the geometry of knowledge. Now, there is one model of knowledge that some of you know called the onion model. Knowledge is an onion, you peel it away, and at the core of the onion is the truth. It's a model which explains nothing and brings tears to my eyes. I like to think of knowledge as expanding in a sea of ignorance, outward, not inward. And that model explains something you all have experienced, namely, the more you know increases as you go to school and do research, but also the more you don't know, ignorance increases, but not as fast, because you're only ignorant of the boundaries of knowledge. The ignorance that's way out there, the so-called unknown unknowns, is inaccessible to you. So, as you all know, the more you know, the more you realize you don't know, but you still get wiser because knowledge increases faster. So this is a good model that explains something, and now let's apply it to a final theory. Is there a final theory? Which is the same question as, is there a finite amount of ignorance? Well, we faced this before in exploring the unknown Earth. This is a map from the Middle Ages, Eurocentric map. The center of the world is in Rome or somewhere. And this is the known world, and the unknown is out there. What we're sort of aware of our ignorance is at the boundary. And if the Earth had been flat, exploration would have gone on forever. But the Earth isn't flat. And with a finite, round, compact Earth, we ran out of ignorance. We have a final map of the world, at least down to a few centimeters or meters. Exploration societies have closed their doors. We have a final theory of geography. Is the sea of ignorance compact? I don't know. I'm agnostic. It could be flat, unbounded, and infinite, and we must keep on exploring our fundamental physics forever. It could be round, compact, and finite, and we will run out of ignorance, and the game will be over. I don't know. I'm agnostic. But I can say that there's no sign of curvature. And we would know it if suddenly began to run out of good questions, good proposals, good things to do, or not at all. Ignorance is still increasing. Anyway, even if we had a final theory in this reductionist sense, this would not be the end of physics by any means. Because reductionism, all physicists are reductionist, but most of physics is exploring the seemingly and probably infinite structures and phenomena that all perhaps are explained in principle by some basic principles. What about our ability to go on? Are we simply too dumb? What arrogance it is to imagine that Homo sapiens, only been around for 100,000 years, are smart enough to understand the principles that describe the beginning of the universe or the structure of space-time. It's pretty arrogant, and we know that our sister species can't. I've been unable to teach my dog quantum mechanics. And we understand that our fellow species cannot answer these questions. Why do we believe that we can? Well, here too I am optimistic, because the tools we have, namely language, mathematics, its highest form, have a certain infinite capacity. Second, there is no sign that we are faced with questions that can't be answered. We would know that experimentally. How would we know it? It would take longer and longer for graduate students to get a PhD. But that's not the case. They still, and many of you that I've met, young, ready to go, as it was 100 years ago, we're not close to the limit of our capabilities. The big worry, actually, is that we may lose the will and the means to go on and the support of society to build these incredibly expensive telescopes and accelerators. And here I can only hope not, and quote Hilbert, "We must know, we will know, and therefore the best is yet to come." Thank you.